Something changed at the exact moment no one expected. As 3i Atlas skimmed the sun, its glow did not rise gently like a normal comet. It jumped. The brightening rate doubled in a heartbeat. The colour shifted bluer than the sun's own spectrum. Space cameras watched a stretched ghost of light with almost no dust at all. Astronomers, Jiang and Batoms, logged the outburst as it unfolded and had no immediate answer. A cosmic visitor broke the rules in full view. We are going to unpack what happened and why it matters. Join the investigation now by liking, subscribing, and staying with us. Start with the simple part. Perihelion means the closest swing by the sun. Many comets brighten as ice turns to gas, sunlight loosens molecules, and pressure inside cracks the surface. 3i Atlas did more than that. Right at the critical moment, its brightness began climbing at roughly double the previous rate. It behaved like a system that hit a switch rather than a stove, slowly warming a kettle. The spectrum added a second shock. The light skewed bluer than the sun's spectrum, a telltale sign of diatomic carbon and amidogen that appear when ices are actively escaping into space. That is the chemistry of a real outburst. It says fresh material was being exposed and vaporized at pace. So far, this sounds like comet physics turned up to 11. Then the images arrived and rewrote the script again. From the Solar and Heliospheric Observatory, from Stereo A, and from the new geostationary operational environmental satellite, the coronagraphs caught a faint, elongated smudge sliding through their fields. The shape looked stretched, as if the coma had been pulled into a spindle. Yet the familiar fan of dust was missing or too weak to see. That is not how a showy comet usually looks under fierce sunlight. Where was the sparkling debris that makes the classic tale? Timing deepened the riddle. Weeks before closest approach, radio measurements implied that 3i Atlas was shedding water at a furious rate. The estimate was roughly 5.7 times 10 to the 28th molecules every second. That was about 40 times more than a month earlier. The numbers scream acceleration. The sequence screams threshold. Physics does allow thresholds, but the precision here is unsettling because the strongest surge happened exactly when the sun should have been cooking everything anyway. Ground observers had little chance to watch that instant. At visual magnitude near 9, small telescopes could have captured it under dark skies. The problem was geometry. The comet sat too tight to the solar glare for Earth-based viewing. Space instruments became our eyes. Coronagraphs block the sun and reveal faint structures around it, so the only clear look at the shape and glow came from orbit. The first takeaways were blunt. A blue-leaning spectrum, a sharp jump in activity, a long but oddly dust-poor appearance. Now the human part. Jiang and Batoms are experienced comet trackers. They have watched hundreds of dusty icebergs do roughly predictable things. This time they wrote that they had no immediate explanation. That is not drama for its own sake. In heliophysics, no immediate explanation means the models on the shelf do not snap into place. You can stretch them. You can add an adjustable knob. They still fall short of matching both the rate of brightening and the missing dust. So, what exactly flipped? One possibility already floats on the table. Far from the sun, carbon dioxide can vent and chill the surface, acting like a temporary shield that suppresses water vapor. Remove enough of that shield, and the deeper water ice sees raw sunlight and erupts. That could be the switch. Yet even that story struggles with the precise timing and the stretched coma without the grit we expect. The question remains, why this object and why this way? We are going to treat this like a shared field notebook. We will follow the data from the outburst into the chemistry, the structure, and the strange images that do not match the postcards in your head. We will keep the numbers clear and the speculation testable. Most of all, we will keep the stakes honest. This visitor may be our best chance in years to watch interstellar material react to our sun. If we read it well, we learn. If we blink, it is gone. To understand the shock at perihelion, we have to slow the moment down and look at the ingredients of the light itself. When a comet is ordinary, its spectrum carries soft fingerprints of gases escaping as the surface warms. With 3i Atlas, the fingerprints were bold and blue-leaning. Diatomic carbon dominated the glow and amidogen was along for the ride. Those molecules form when fresh ice gets ripped into space and torn apart by sunlight. The message is simple. New material was exposed fast enough to change the color of the entire scene. Numbers added muscle to the picture. Radio measurements in the 2 weeks before closest approach pointed to a water loss rate near 5.7 times 10 to the 28th molecules every second. That is a mountain of water molecules, not a trickle. 1 month earlier, the estimate was roughly 40 times smaller. You can feel that escalation in your bones. Something accelerated inside the nucleus, or just beneath its skin, and the curve bent upward hard. Now bring in the cameras that could actually see in the sun's blinding neighborhood. The Solar and Heliospheric Observatory, known as SOHO, blocked the solar disk with a coronagraph and revealed a thin, stretched glow where we might expect a broad, dusty fan. The Solar Terrestrial Relations Observatory, known as Stereo A, added matching views from a different angle. The new Geostationary Operational Environmental Satellite 19 put eyes on the same corridor as well. Across instruments, the shape ran long and faint, like a spindle sliding away from the glare. Dust was not taking a bow in the way. Comet watchers are used to seeing. That is where the paradox sharpens. The chemistry screams that ice is turning to gas with enthusiasm. The water numbers shout that the rate of loss is off the charts compared with a month earlier. Yet the classic dust tail is absent or very shy. In a normal show, those three elements travel together. Heat a nucleus, vent gas, drag grains of dust into sunlight, and you get the luminous fan that carries so much romance in human memory. Here the gas plays headline act, while the dust stays backstage. Either the dust is unusually scarce, or the grains are too large to scatter, visible light, or the ejection pattern is strange enough to smear the signal into a skinny thread. Perihelion itself matters for timing. At closest approach, the sunlight is brutal, and the temperature gradients can flip internal processes from slow creep to runaway escape. A collapsing shield of carbon dioxide is one clean explanation. Farther from the sun, carbon dioxide can vent and cool the surface, forming a temporary stabilizing layer that mutes water sublimation. As that layer thins with time, buried water ice finally sees unfiltered radiation and the system jumps to a new regime. That story fits the chemistry, and it fits the rise in water output. It does not effortlessly explain why the comet looked dust poor while the gas roared. Brightness behavior adds one more wrinkle. The rate did not merely rise, it roughly doubled relative to its prior trend, and it did so right when the geometry made ground-based viewing nearly impossible. At about magnitude 9, it was within reach for hobby telescopes under dark skies, but it hugged the sun so closely that only space instruments could watch the key minutes. That removed the chance for a swarm of amateurs to catch fine structure, and left us with a handful of vantage points. The data we do have are good, but limited perspectives always leave room for competing interpretations. When modelers try to fit all of this, at once they run into a wall. Simple sublimation curves, even with a shielding layer that fails at a threshold, do not easily match a surge that's steeped together with a coma that looks stretched and dust-shy. You can tweak the size of the grains, you can change the porosity of the surface, you can tilt jets and play with spin. Some combinations get close on one metric and drift on another. That is not failure. It is the universe telling us to refine our questions. What exactly changed at perihelion is likely a stack of causes, rather than one neat switch. A processed outer rind may fracture along old radiation scars. Trapped gases can find pathways at once. Sunlight can punch through a thinning shield and strike an ice-rich pocket that vents like a fire hose. Put those together, and you get a sudden blue-leaning bloom, a flood of water, and a coma stretched by anisotropic flow. The dust mystery remains the outlier that keeps minds awake at night. Until we see the post-perihelion, evolution in detail, that missing sparkle is the thread that refuses to be cut. Take the cleanest natural story first. Far from the sun, carbon dioxide can escape from a porous nucleus and frost its own surroundings, chilling the surface and sealing microfractures. That makes a temporary shield. The shield slows water ice from turning into gas, so the comet looks calmer than it really is. As sunlight grows harsher, that shield thins, pores reopen, and deeper layers suddenly see raw radiation. In that instant, the system flips from muted to roaring. That is the collapsing shield hypothesis in one breath. It is attractive because it explains three key clues at once: an abrupt switch in activity instead of a gentle climb, a spectrum rich in diatomic carbon and amidogen as fresh gases flood space, a stretched, gas-dominated glow if vents channel the outflow in narrow streams. The shield also gives us a simple picture for threshold behavior. Hold the line while carbon dioxide remains abundant. Lose the line when it is gone. Yet timing gets thorny. Why did the flip land almost exactly at perihelion and not a day earlier or a week later? Real comets carry thermal lag. Heat takes time to soak through a crust, and the depth that fills the day is shallow compared with the size of the body. If heat lag ruled, the peak might arrive after closest approach, not right on top of it. Rotation adds more texture. A spinning nucleus bleaches one face, then another, and the most active vents often breathe in pulses. That can sharpen bursts, but it does not guarantee a perfect match to a single moment. Now look at the missing dust. Normal outbursts loft grains that scatter sunlight and paint the classic fan. Here the gas shouts while dust whispers. There are natural ways to mute that sparkle. The surface could be unusually ice-rich and rocky poor. The grains could be large, dark, or bound together so they do not drift far enough to make a bright fan. The gas could exit through tight jets that stretch the coma into a slim spindle, while heavier grit falls back. The irradiated crust suggested by James Webb can also act like a filter, trapping or compacting particles until pressure crosses a breaking point. If the shield story is right, it should leave tracks we can test. The ratio of carbon dioxide to water should evolve in a specific way as the shield fails and water takes over. The color of the glow should tilt as new species dominate, then relax as the system settles. Hydroxyl emission from broken water ought to bloom just after the switch. Light curves should carry hints of rotation as vents sweep across our line of sight. Plasma cameras should catch the solar wind carving consistent shapes from a set of jets rather than a broad dusty cloud. Modelers have been busy. They try different grain sizes, different porosities, different spin states, and networks of fractures that connect or clog. Many runs can match one piece of the puzzle, a few match two. Almost none match everything at once. The combination of a doubled brightening rate, a blue-leaning spectrum, and a long dust-shy profile is the stubborn triad. Collapse the shield, and you get the switch. Add rotation, and you get modulation. You still need a reason for dust to hide while gas goes wild. There is also the location of weak points to consider. A nucleus aged by cosmic rays may be quilted with brittle seams that crack in families rather than alone. If several vents opened within hours along an old radiation scar, the outflow could leap without warning. In that picture, perihelion is not a magic trigger. It is simply the first time sunlight and internal pressure climb high enough together to pop the seam line. That gives you a near-perfect coincidence without invoking anything beyond structure and stress. So, where does that leave the collapsing shield? Still viable, still elegant, but incomplete. It answers why a switch exists, and it sketches why the gas led the show. It does not yet lock in the perihelion precision or the anemia of dust. The only honest move is to keep testing. Watch the ratios, track the color, measure the cadence. If the shield failed, the comet should now relax in a way that follows distance from the sun. If it does not, the timing problem remains a live wire, and the search for deeper causes continues. The picture changed when the James Webb Space Telescope weighed in. Its near-infrared spectra did not just tally familiar comet gases. They hinted that the outer layers of 3I Atlas have been rebuilt by the galaxy itself. In interstellar space, there is no protective bubble like our heliosphere. High-energy particles roam freely and strike anything that drifts for long enough. Over millions and billions of years, those hits do chemistry. They break bonds, shuffle atoms, and reassemble the surface into new compounds. Models built from laboratory ice experiments and computer runs say that this processing can reach dozens of feet into a small body. Think less of a fresh snowball and more of a weathered armor. That armor matters. It can convert carbon monoxide into carbon dioxide, change the texture from fluffy to compact, and seal pore spaces that once allowed gentle breathing. It can darken and harden the crust while leaving different ices trapped below. When sunlight finally warms such a skin, the behavior is not a simple melt. Pressure builds behind the processed rind until a fracture offers a path. Then everything looks abrupt. That is exactly what the perihelion surge felt like. There is strength in the idea that we were not watching a primordial face. We were watching a travel scar. James Webb spectra also help us parse the color story. A blue-leaning glow can come from strong emission bands of molecules produced when fresh gas escapes and sunlight tears it apart. If the surface is processed and tight, the first cracks expose pockets that have been sheltered for eons. Those pockets can be rich in the molecules that light the blue bands. The result is not a slow drift in color. It is a pivot as a new set of species begins to dominate the light. The irradiated crust changes more than chemistry. It changes mechanics. A compact, cemented shell resists the easy lofting of loose grains. That naturally mutes the dust and could explain why the coma looks stretched and faint rather than broad and sparkling. Gas can whisper through microchannels with little grit in tow. It can also rip through a fresh break in a narrow jet that draws the glow into a spindle. Both pictures match the images we have so far. The dust-poor look becomes a feature, not a bug. There is a deeper implication that cuts to the heart of why we chased interstellar visitors in the first place. For years, we dreamed that a traveler from another star would carry a pristine sample of its birth system. James Webb suggests the opposite on the outside. The skin we can most easily see may tell us more about the journey than the origin. That does not kill the dream, it moves it inward. The question becomes how far the processing goes and how quickly our sun can erode the rind to reveal interior material that still whispers of home. This is where the timeline matters. As 3I Atlas moves away from the sun during the coming weeks, the balance between processed crust and exposed interior should evolve. If the armor is thin, continued heating, near Perihelion, may have peeled it back, and we should see fresh compositional signatures appear as new vents open. If the armor is thick, the object may relax and fade in a way that tracks distance from the sun with little change in spectral mix. Both outcomes are informative. One tells us about a thin shell over a volatile heart. The other tells us about a traveler transformed almost through and through. We can test this story with coordinated watching. Track the ratio of carbon dioxide to water day by day. Watch the blue bands that flag freshly exposed gas. Map the light curve for signs of rotation that would steer a small number of jets. Compare coronagraph images for changes in coma shape that hint at new fractures. If the irradiated crust model is correct, we should see rhythms that mirror structural limits rather than a fully free breathing snowball. The physics of armor leaves fingerprints in timing as well as color. There is a poetic twist in calling a comet armored. It suggests intent. Here it is, purely natural. Radiation built the shell without asking. The shell kept the traveler intact, then set the stage for a dramatic reveal when it finally met strong sunlight again. That is the story James Webb invites us to test. A visitor wearing an ancient suit, hiding a core that may still remember another sun. If we read the layers with care, the armor does not block the truth. It points the way toward it. The most important clock started ticking, the moment 3I Atlas rounded the sun and began to drift outward. Brightness will change. Colors will evolve, jets may shut down or new ones may punch through. All of that is a moving target, and our chance to catch it is measured in weeks, not years. Perihelion gave us the shock. The aftermath will tell us whether that shock was a one-time pop or the beginning of a pattern. Windows like this close quietly. You only notice when the data stream goes thin and the visitor fades into static. Space-based eyes remain our lifeline. Coronagraphs continue to blot out the solar disk and reveal faint halos and threads in the glare. The Solar and Heliospheric Observatory still patrols the corridor. Stereo A continues its offset vantage that lets us see shapes from another angle. The newest geostationary satellite adds fresh coverage as the glow slides outward from the danger zone. Each camera sees with different filters and sensitivities, which means the truth emerges from overlap rather than any single hero image. Water leaves a distinct calling card. When sunlight breaks water molecules, fragments radiate in ultraviolet light that we can measure. The swift ultraviolet and optical telescope already picked up the hydroxyl glow. That emission should rise and fall with real outgassing rather than wishful thinking. If the eruptive switch was a one-shot event, the hydroxyl signal should crest and then decline smoothly as distance grows. If the surface continues to open new vents, the signal could wobble or even trend upward before it falls. Either way, ultraviolet light will keep us honest. The solar wind writes invisible graffiti on every comet. Charged particles stream outward from the sun and run headlong into the expanding gas around a nucleus. That confrontation makes boundaries and waves that depend on what the coma is made of and how strongly it flows. Plasma imagers can trace those shapes. If 3I Atlas is driven by a handful of narrow jets, rather than a broad outflow, the wind should carve crisp asymmetries that repeat with rotation. If the coma is nearly dust-free, the structures should look lean and smooth compared with the ragged fans seen in dust-rich comets. There is also the geometry advantage we rarely enjoy. Mars rovers have a slightly different line of sight than Earth-bound or Earth-orbiting instruments. Even a small change in perspective can fix ambiguities about whether a narrow jet points at us or away from us. Triangulation turns guesses into maps. If those rover images are processed and shared quickly, we get a better three-dimensional sense of how the coma is organized and how it evolves day by day. Now the part that is as human as it is technical. A limited window demands more than curiosity. It demands coordination and openness. When only a few instruments have the necessary view, the risk is that data stays siloed while the clock runs out. That is why the call for full public release matters. Raw spectra, calibrated images, time-tagged light curves, and pointing, information in formats that independent teams can use without friction. Put it all on the table so that professional groups and committed amateurs can split the problem and cross-check results. Open data is not charity. It is a force multiplier. Anomalies often hide in the gap between instruments and methods. One team might see the color swing, another might trace the light curve pulse that marks rotation. A third might notice that plasma structures lock to a cadence that does not match simple heating. No single pipeline is perfect, and no single modeler sees every corner. The crowd does not replace expertise. It composes it. There is also an ethical clarity to transparency when an interstellar visitor is involved. This is not a private laboratory sample. It is a shared natural experiment that will not repeat. The most responsible move is to let many minds test many hypotheses quickly and in the open. If the simplest explanation wins, we will know it is robust. If the data keep refusing easy answers, the field will already be organized to ask better questions. So the narrow window is a challenge and an invitation. Keep coronagraphs rolling. Keep ultraviolet eyes on the hydroxyl glow. Watch the solar wind carve the coma for signs of jets and rotation. Press for rapid releases that include uncertainties and calibration notes. Most of all, accept that clarity in science is often a social achievement. When the object is already leaving, the only way to capture the truth is to let more people hold the net. Step back from the drama of an outburst and ask a bigger question. What are interstellar objects for in the story of the galaxy? Some researchers argue they are not just leftovers, they can be seeds. Young stars live inside wide disks of gas and dust where pebbles collide and grow. That growth stalls when rocks reach about a meter across. At that awkward size, they spiral inward or shatter in traffic. The disk is turbulent and drag is fierce. Worlds need a way to skip the bottleneck. Here is the bold idea. The galaxy supplies ready-made kernels. Interstellar bodies drift through a newborn system. The gas in the disk slows them. Gravity does the rest. A visitor hundreds of meters wide can be captured and parked on a stable orbit. Once it is resident, the disk begins to feed it. Pebbles and boulders collect. Gas flows around the new center. Suddenly, the meter barrier is gone because the seed is already far larger than the dangerous size. This picture explains a lingering mismatch in planet formation. Observations show gas giant planets are common around stars that burn hot and fast, yet their disks fade within a few million years. Traditional models struggle to build a giant that quickly from tiny grains alone. Seeds change the schedule. With a head start, the core gathers mass at a pace that fits the lifetime of the disk. Where seeds are common, giants can be common too. How does 3I Atlas fit into this? Its speed and path tell us it is the kind of object that can wander for eons between stars. Its mass is large enough to matter inside a young disk. Its armor of irradiated crust may even help it survive the chaotic entrance. If caught by gas drag or resonances with growing planets, it could have taken a seat near the midplane and begun to accrete. In another timeline, this drifter might have become the heart of a world. Capture is not magic. The disk must be dense enough at the right place and time. The incoming angle must let the gas do real work. The visitor must lose just enough energy without being torn apart. Yet simulations show that when a star is young and the disk is thick, the odds are surprisingly friendly. Millions of interstellar passers-by cross a volume of space over the life of a cluster. Even a small capture fraction yields many seeds. There is a human reason this resonates. It reframes debris as potential. A shard that missed its chance is not a failure. It is a sample of the raw, ingredients that can build landscapes and skies. If 3I Atlas carries a core that remembers its birth, then we are looking at the kind of nucleus that could have anchored a future moon or a future giant. The romance of that idea is not fluff. It directs the questions we ask and the measurements we prioritize. The seed picture also turns our attention to composition in a new way. A captured object that already carries complex ices and organics can enrich the disk locally. It becomes a chemical hotspot around which pebbles inherit new mixtures. The hard irradiated rind we see today would have been a bonus inside a young disk. It would have protected the interior through the first rough 1,000 orbits until accretion built a thicker blanket of material. None of this makes 3I Atlas unique. It makes it typical of a hidden population. The galaxy could be swarming with ancient kernels that sometimes miss and sometimes stick. Most never meet the exact conditions required for a pair. Safe capture. A few do. Those few change the architecture of a system and tilt the odds toward planets where time would have run out. Seen through that lens, the current outburst becomes more than a spectacle. It is a stress test of a seed under solar conditions. We are watching what a potential planet core does when a star turns the heat up. We are learning which layers break first and which gases take the lead when armor opens. Every ratio and every light curve we record today feeds back into the models of how seeds behave inside disks. We are not just gawking at a comet. We are rehearsing the birth of worlds. So is this visitor mere debris or a seed that missed its moment? The fair answer is both. It is a leftover from long ago and far away. It is also the right size and nature to have anchored a planet if fate had nudged it into a different disk. That dual identity is why this observation window matters. We can treat a fading glow as an ending, or we can treat it as a lesson on how beginnings really work. To understand a traveller, follow its path. 3I Atlas did not meander through our neighbourhood like a comet raised among the planets. It sliced through on an unusually flat and steady approach, as if it had trained for straight lines across empty space. That calm geometry is the first clue. Bodies born here carry the scuffs of repeated encounters. They loop, they kink, they bear little nudges from planets that have tugged them for ages. This visitor looks less coached by our family and more shaped by a much longer journey. Speed adds the second clue. Relative to the solar system, it is moving near 130,000 miles per hour. Fast enough that escape is a given, yet not so fast that it ignored the sun entirely. That range of speed is the calling card of interstellar drift. Too quick for capture by a single pass, slow enough to let the sun's light and wind draw out the hidden story as it flies. With that velocity, you can cross the gulf between stars with time to spare. Age is the third and most humbling clue. Some estimates place this object between 7 and 12 billion years old, older than Earth, older than our sun. That span covers eras when the Milky Way itself was settling into the spiral we know. Imagine the parade of environments it has crossed. Regions rich in heavy elements, deserts stripped by stellar winds. Neighborhoods of newborn suns wrapped in bright disks. Every mile added wear, every century added scars, and still the body holds together enough to carry a memory into our sky. Survival demands a mechanism, and the irradiated crust provides one. A deep layer processed by cosmic rays can compact, harden, and shield the interior. Under that armor, pockets of volatile ice and trapped gases wait. The outside does not need to be pretty to do its job. It only needs to endure. When the traveler finally meets a strong star again, stress rises, fractures connect, and the inner chambers speak. That is how a drifter, older than our planet, can still surprise us with a fresh outburst in the heat of today. Where did it start? The straight approach and high speed imply a launch far from major gravitational landlords. Perhaps an outer region of a young system where giant planets were fighting for territory. Ejection is a common fate for small bodies in those brawls. A swing past a massive world adds energy and flings the loser into the black. Another path begins at the edge of a star cluster, where tidal nudges are gentle but relentless. Give a small object enough small kicks and it will eventually slip the leash and join the wider sea. There is also the question of chemical dialect. If the outer layers are rebuilt by radiation, then clues to the home system sit deeper inside. The elements and ices laid down at birth carry the accents of the parent star and the nursery disk. Ratios of carbon-bearing molecules, the balance between water and more exotic ices, isotopic fingerprints that act like passports. We may never drill this body, but changing spectra as sunlight erodes the armor could still whisper of origin. The map we can draw today is simple but not empty. A near straight path through the inner system, a velocity that makes this visit brief, an age that stretches belief and forces respect. Put those together, and you get urgency. We are not watching a local seasonal show. We are watching a messenger from deep time sprint past our door. If we do not harvest every bit of light and timing and shape while it is here, the chance will not circle back. This is the kind of object that writes its own deadline into the sky. There is comfort in that pressure. It focuses the mind, It turns speculation into test lists and hunches into schedules. Track the path precisely to watch for tiny pushes from outgassing. Time the light to catch rotation. Scan for shifts in molecular bands as the sun works the surface. Each piece of the plan leans on the same truth. The drifter is already leaving. The only way to honor a traveler this old is to meet its speed with our own. Speculation is only useful when it points to a measurement. The bold idea on the table is engineered activation. If a traveler were meant to survive the gulfs between stars, an armored rind created by radiation would be a gift. The shell would shield the core for ages, then crack and wake interior processes only when the object dipped through the fierce light and charged particles near a star. That sounds cinematic. It is also testable. The way to treat a provocative thought is simple. Turn it into a checklist that nature can pass or fail. Start with thresholds. Natural heating tends to make smooth curves. When sunlight rises, sublimation rises, with bumps from rotation and fractures. An engineered trigger would favor sharp steps at specific conditions. Look for a repeatable switch as solar energy crosses the same level again during the outbound leg. Watch for activity that stays quiet until a narrow range of solar flux is reached and then snaps on. If the curve shows a crisp staircase rather than a hill, the door to design stays open longer. If the curve rounds off the way ice normally behaves, that door closes. Next comes motion. Outgassing pushes like tiny thrusters and can nudge a path. In natural cases, the push lines up with visible jets and with the cadence of rotation. If a non-gravitational acceleration appears that does not match the direction or timing of observed vents, we have a mismatch. Track the orbit with absurd precision. Compare the momentum budget implied by the gas that spectra actually measure with the momentum shift we see in the path. If there is thrust with no propellant visible, that is interesting. If every wobble is explained by jets we can see and quantify, that is natural. Structure can whisper intention. A rubble pile that grew from chance collisions tends to have irregularities and messy symmetries. An object built to endure would favor repeating patterns in strength and fracture lines. We cannot photograph the nucleus at leisure, but we can read patterns indirectly. High-cadence light curves reveal shape through the way brightness pulses as the body spins. Polarization measurements of the coma encode the size and organization of particles that leave the surface. If we find persistent, neat symmetries in the way jets switch on and off that ignore the usual solar geometry, that would be a flag. If the pattern follows simple sun-chasing physics, chalk it up to nature. Noise matters too. The solar wind can make radio static, and the coma can sing with plasma waves, but those signals sit in known bands and drift with known rules. A design system that speaks would likely favor narrow lanes and repeated features that do not care about the local wind. Point radio ears across a wide dial. Search for narrow and stable features that persist when the solar wind changes temperament. Cross-check for sidebands or modulations that follow no natural clock we can name. Expect null results and demand strong evidence for anything else. Thermal behavior is another honest witness. Instruments that sense heat can watch the surface respond as day and night sweep across the nucleus. A natural body warms and cools with a lag that depends on density and porosity. A device that shunts heat or reroutes it for internal work would look odd. Seek patches that stay too stable in temperature while neighbors swing wide. Look for cooling that is faster than conduction allows, as if energy were being moved inward. Chemistry gives us perhaps the cleanest yardstick. Nature leaves ratios. The balance of water, carbon dioxide, and other volatiles should evolve smoothly as the surface erodes. A system that meters out species on demand would create plateaus or repeating packets in the spectra that ignore the slow roll of distance from the sun. If we see controlled rations, that is a clue. If we see the continuous blends shaped by sunlight and stress, the mundane wins. There is also the question of aftershocks. When a natural shell fails, fractures propagate, and then the system typically quiets as pressure drops. If we watch a series of pulses that arrive at equal intervals like a heartbeat, or if the intervals lock to a period that is not the spin and not the day-night cycle, that would demand fresh thinking. Time, the pulses. Compare them to rotation. Compare them to the changing angle of sunlight. If they refuse to line up with any of the above, circle them in red. All of this protects us from story-first thinking. The way to handle a dramatic idea is not to sell it, it is to try to break it. 3i Atlas gives us the tools. Light curves for timing, spectra for chemistry, plasma images for wind and jets, precise astrometry for hidden thrust, Radio sweeps for whispers we do not expect. If every test lands on the side of natural thresholds and messy geometry, we learn and move on. If even one test refuses to fit, we do not declare victory. We sharpen the next test and keep going. That is how speculation earns the right to stay in the room. The next few weeks are where guesses meet daylight. If 3i Atlas is simply cooling after a dramatic switch, the light should settle into a smooth decline as distance from the sun grows. The color should drift back toward normal, and the chemistry should ease from the shock of fresh vents to the steady breath of a tired traveler. That path would favor the collapsing shield and irradiated crust picture. Quiet, graceful, predictable. If instead, brightness wobbles, if color flips in pulses, if new gases arrive in packets, then the surface is still changing in ways distance alone cannot explain. That would point inward, towards structure and processes that do not care about geometry. We can stage this like a rolling experiment. Night by night, build the light curve with enough precision to see small steps, rather than just the big slope. A rotating body paints its spin into that curve. If a handful of jets dominate, the rise and fall will repeat at the same interval until fractures migrate or shut down. A pattern that holds steady is a win for natural venting. A pattern that shifts off the expected cadence or repeats in neat intervals that ignore spin is a problem worth chasing. Spectra tell the second half of the story. Watch the balance between water and carbon dioxide day by day. A shield failure that exposed deeper ice should produce a burst of water signatures that peak and then relax. If those signatures instead arrive in bursts that keep pace with nothing but themselves, we learn that new chambers are opening on their own schedule. Monitor the blue-leaning bands that lit up at Perihelion. They should fade as the wildest gas clears. If they hold or swing back, the interior is not done talking. Shape matters, even when the nucleus hides in glare. Coronagraph images can map the fin halo and any thin spindles that mark narrow jets. Compare frames from different instruments to remove the tricks of viewing angle. If the coma stays long and dust poor, then the dust story holds and gas remains the headliner. If a broad dusty fan finally blooms, it means the armor has yielded and grains are free to ride the flow. That change would confirm that we have pushed through crust into more typical comet behavior. The solar wind serves as both sculptor and snitch. Plasma images capture boundaries and waves where wind meets gas. Those structures are sensitive to the number, strength, and direction of jets. If rotation is imprinting a rhythm, the boundaries will breathe with that rhythm. If a new vent wakes, the pattern will hiccup and recover. A clean and repeating pattern is comfort for the natural camp. A pattern that carries beats we cannot tie to rotation or to the day and night cycle needs more attention. Astrometry quietly ties the physics together. Track the path with a absurd care. Outgassing thrust will nudge the trajectory in predictable ways if it is driven by observed jets. Compare the momentum we infer from spectra with the momentum the path demands. If the numbers add up and the vector lines up with the visible outflows, nature is winning the argument. If the path demands extra push from nowhere, the investigation stays open. There is also a social lever we can pull. Rapid releases of calibrated data let many eyes look for patterns no single pipeline is tuned to catch. Amateurs with small telescopes can contribute light curves from longitudes professionals cannot cover. Students can mine public images for subtle shape changes. Specialists can fold plasma, spectrum, and orbit into a single timing diagram that leaves as little ambiguity as possible. The point is not to vote on explanations. It is to compress the time between anomaly and answer while the window is open. In a month or two, the arc will be clearer. Either the curve has relaxed into distance-driven physics, or it has kept its own strange beat. Either the spectrum has drifted back toward ordinary, or it has continued to flash new clues. Either the path is fully explained by jets we can see, or there is momentum we cannot account for. The beauty here is that ambiguity is temporary. The sky makes us a promise. Keep watching with discipline, and the story will pick a lane. A single traveler can change the way a field thinks, not because it is loud, but because it refuses to fit the mold you built from easier cases. 3i Atlas has done its part. Now the responsibility shifts to us. We have to decide whether we treat anomalies as noise to be sanded away or as signals that force better questions. That choice is cultural as much as technical. It decides whether the next interstellar visitor finds us ready with a sharper playbook or stuck rehearsing yesterday's script. Start with humility. Our archive of confirmed interstellar guests is tiny. First came Oumuamua, a shapeshifter that left as arguments trailed behind it. Then came Borisov, more familiar and yet clearly born under a different sky. Now, 3i Atlas, a drifter with armor and timing that press our models. 3 objects across years is not a data set, it is a hint. When samples are this small, dogma is a luxury we cannot afford. The only safe posture is open hands and sharp tools. Rigor is the other half. Curiosity without discipline turns speculation into theatre. The way we win trust with the audience, and with one another, is to make claims that lean on measurements anyone can check. That means clean reductions, clear uncertainties, and methods that hold up when strangers run them. It means turning eye-catching ideas into tests that either pass or fail, and accepting the verdict even when it stomps on a pet theory. The power of a bold narrative is real. The power of a reproducible plot twist is greater. Transparency is the hinge that lets humility and rigor swing together. Rapid releases of spectra, light curves and images are not favors. They are the shortest path to truth. When data move fast, creativity multiplies. Independent teams find cross-checks the originators did not imagine. Students catch patterns a senior group dismissed because they look like instrument quirks. Amateurs add time zones that fill gaps in professional schedules. None of that is chaos. It is a distributed sensor for insight, and it works best when the clock is ticking. Our tools have finally caught up with our ambition. The James Webb Space Telescope can read chemistry that once lived only in laboratory wish lists. Continuous heliophysics images paint the space near the sun with a cadence that used to be impossible. Ultraviolet telescopes measure the breadth of water by tracking hydroxyl fragments. Radio arrays can sweep wide swaths of dial to listen for narrow features against the storm of plasma noise. Tie these together with precise astrometry, and we can watch, not just glitter, but momentum. We can see how light, gas, and motion add up. The next step is procedural. Treat every anomaly as an experiment that can be repeated in principle, if not in time. Pre-write the tests before the data tempt you. Publish the plan so the community can point out blind spots. Share intermediate products with enough context that others can replicate the path. If a result depends on one calibration step or one background subtraction, make that step boring by explaining it well. Great science turns drama into method. It leaves as little of the surprise as possible to personality, and as much as possible to measurement. We also need the courage to hold more than one hypothesis in our heads, without letting ego pick a winner early. The natural shield story and the irradiated crust story are strong. The designed activation idea is provocative and only earns its seat if it survives hard tests. The point is not to crown a narrative. It is to let reality select. That posture keeps us honest in front of the audience that trusts us to separate wonder from wish. 3i Atlas will fade, the light curves will flatten, the coma will thin. The memory can still be productive if we let it change how we work. Build open pipelines that expect surprise. Train ourselves to look for thresholds, not because they prove design, but because they sharpen explanations of nature. Normalize saying we do not know while laying out exactly how we plan to find out. Celebrate the null result that closes a door with the same conviction we reserve for the dramatic one that opens it. There is one more reason this matters. Objects from other stars do not just teach us about distant chemistry, they teach us about time. Each visitor is a note from a different chapter in the galaxy's long story. Reading those notes well demands patience, agility, and a willingness to stand on the edge of uncertainty without flinching. That is a skill set as worth building as any instrument. This is the promise. If we handle this visitor with humility, rigor, and transparency, the next one will not catch us off guard. We will have the tests ready, the channels open, the community warmed up, and the courage to let evidence lead. The universe is sending messages in the only language it knows: light, motion, and chemistry. Our job is to become fluent enough to listen without imposing our accent. If we do that, a single traveler will have changed not just what we know, but how we learn.